Hello everyone, in this video I explain applications of Newton's second law, apparent weight. Let us restart.
When a body is kept on the platform of a weighing machine, its weight is given by the normal contact force between the body and the platform of the machine.
If we have weighing machine, this is the platform of weighing machine, and a person standing on that weighing machine. So that is the person standing off the platform of weighing machine. We have here two forces act. First, the weight of the person acted downwards, and the normal contact force from the platform of weighing machine, the normal contact force. If the weighing machine is stationary on the floor, on the ground, so the normal contact force equals the true weight of the person. So the normal contact force equals the true weight of the person. Now, if we take that weighing machine and put it in at the floor of elevator, this one here, it's inside elevator. So this is an elevator. We have four cases. First case, when the elevator at rest. So at rest. So in that case, when the elevator at rest, the normal contact force equals the true weight. The second case, when the elevator moves upward with acceleration, constant acceleration A. We apply Newton's second law, sum of F equals ma. So R minus W equals ma. In this case, R, the normal contact force, is greater than the true weight. So the apparent weight here is greater than the true weight. In the third case, if the elevator moves down, so W minus R equals ma. In this case, if it moves down, so R less than the true weight. So the apparent weight in this case, when the elevator moves down, the apparent weight, it will be less than the true weight of the person. The fourth case, if that elevator falls down with acceleration g. In this case, actually, R equal to 0. R equal to 0. This case is called the weightlessness. So in this case, the apparent weight equal to 0. In the fourth case, the apparent weight, it will be 0. So that are the four cases. Let us take example. The diagram shows the forces acting on a person in a stationary lift. The person has a mass of 70 kilogram. Taking G equals 10 Newton per kilogram, calculate the contact force R when part A, the lift is at rest, part B, the lift is accelerating upwards at 1.0 meter per second squared, part C, the lift is accelerating downwards at 2.0 meter per second squared, part D, the lift is ascending at a steady speed. Now, the given for the first part, it is at rest. First of all, the given in that, the mass of the person, it's 70 kilogram, and the acceleration of gravity, it's 10 meter per second squared, or 10 Newton per kilogram, is the same. That are the given. The first case, the lift is at rest. The resultant force equal to 0. So R equals W. R equals the weight. The weight equals mg. M is the mass of the person, which is 70, G equal 10, so it is 700 Newton. So R equals 700 Newton. This is the R, the normal contact force. Part B, he said, the left is accelerating upwards at, so the left accelerating upwards at A equals 1.0 meter per second squared. We apply Newton's second law. Sum of F equals ma. Moves upward, so R is greater than W. The normal contact force is greater than the weight. So we write the equation as R minus W equals ma. We need R. In each case, we need R. So R minus the weight, it is 700. M, it is the mass, which is 70. Multiply the acceleration in that part, the acceleration 1.0 meter per second square. So multiply by 1.0. Rearrange this equation to get R. So it is 70 multiply 1 plus 700. It is 770 Newton. So this is R in part B. In part C, it says the lift is ascending downwards. So now we go to part C. The elevator or the lift, he said the lift is ascending downwards at 2. So the acceleration, it's 2 meter per second squared. When it moves down, the weight is more than the normal contact force. So Newton, the second law, sum of F equals ma. So W minus R equals ma. W is the weight, which is 700, minus R, the required, equals M 70 multiplied by 2. Rearrange this equation, so move negative R to the other side. So it is 700 minus 70 multiplied 2 equals R. 700 minus 2 times 7, 14, so 14 cents equals R. We do this subtraction, so downwards it will be 560. So R, when we calculate this, it will be 560 Newton. So this is the normal contact force in part C. In part D, he said the lift is ascending at steady speed. Steady speed, it means the acceleration equal to 0. When the acceleration equal to 0, the resultant force equal to 0, so R equals W, so R equals 700 Newton. So that are the 4 cases in that example. So in the first case, when it is at rest, R equal 700. It is the same as steady speed. So the normal contact force is 700. The second case, when the lift moving upward, the normal contact force increases. It's more than normal contact force, we said before, it is the apparent weight. So the apparent weight is more than the true weight. This is the true weight when the elevator or the lift at stationary. The apparent weight is that one. So the apparent weight is more than the true weight. At stationary, the apparent weight and the true weight the same. In the part C, when it moves down, R equals 560 Newton. It is less than. So the apparent weight is less than true weight. So the apparent weight less than the true weight. In that one, when it moves, the lift moves at a steady speed, so the acceleration equals 0, so the resultant force equals 0, R equals the weight. So also at steady speed, the same as stationary, the apparent weight equal the true weight. I hope you understand this application. Thank you.
You step into an elevator. It starts going down fast. What would happen if you jumped right when it started going down? Would the ceiling hit your head? Ouch. Do you stay suspended in the air while the elevator plummets down? Let's examine the elevator problem one step at a time. First, the elevator is standing still, so you and the scale are standing still. The two forces on you are equal and opposite. Well, you can read how hard the scale is pushing by looking at it. We call that your weight. Then the elevator starts falling down. You and the scale are in the elevator, so you are falling down too, faster and faster. That means you are accelerating downward. Now there is a net force in the same direction as the acceleration, down. Since gravity hasn't changed, that must mean the scale isn't pushing up as hard. So the scale is reading a smaller number. The faster the elevator accelerates, the less the scale pushes up. But if you jumped, would you stop falling? Would the elevator hit your head? Well, what's pulling the elevator down? Gravity. Is gravity pulling on you? Of course. So your relative position in the elevator will stay the same. The ceiling will only hit you if you can jump up to the ceiling. Now consider what would happen if the elevator accelerated upward. And even more frightening, if someone snuck in and cut the cable holding the elevator, what would happen then? Think about it.